All right. So what we were talking about yesterday is the idea of a series versus a sequence. Oh, thank you. And I'm not presenting at home either, I don't think. And what we talked about is you get a general term for both of them. The sequence is just listing those out. And then a series is then not just listing them, but also finding the sum of all of them. So for number 14, what we were talking about first and foremost is this a geometric series that converges? So this one isn't quite as obvious that it's geometric. So let's kind of go through with plugging in these first couple of points, even though I said we kind of want to graduate from that and be able to just look at it and be able to go to it. So if we were to plug this in, I would get the cosine of 0 first, so that's going to be a 1. And then I would get 5 to the 0, which is also a 1. And then we know we're going to add, since it's a sigma, we're going to find the sum. If n is a 1, what I end up with is the cosine of 1 pi, which is a negative 1. And then I would get 5 to the 1. If we go to the n value of 2, now it's cosine of 2 pi. I'm back to a positive 1. 5 squared is 25, and we'll do one more to see, make sure we see the pattern. If n is a 3, I now get cosine of 3 pi. So now we're all the way back over at regular pi, single pi. So that's a negative 1. And then 5 cubed is 125. So what you're going to notice, it's really obvious if we go back to one that we've done, like here, when you have a little negative 1 to the end, that this is one of these alternating series, it's going to bounce back and forth, positive, negative, positive, negative. This is another one that will do this. So the cosine of n pi is another one that would show that we're going to be alternating back and forth, right? So with this, what we then talked about yesterday, this is a geometric series. So we started talking about what's our ratio, and that's just the number that we're multiplying by, although this you did in past years, to get that subsequent term on down the line. So to go from 1 to a negative 1/5, positive 1/25, so on and so forth, we would say that we are multiplying by a common ratio of a negative 1/5. Then we talked yesterday that this will have a sum, this will converge to a sum if the absolute value of our ratio is less than a 1. So pretty clearly, you don't necessarily want to change this on yours, but the absolute value of this definitely is less than a 1. So this should converge, and then it should converge to this sum here. A sub 1 represents the first term. So as we listed all of those out, that would have been a 1. Over 1 minus our common ratio, that's that negative 1/2. Or sorry, 1/5. So we get 1 over 6/5. If we were to start adding those terms up into your calculator, you would see that those start getting closer and closer and closer to 0.83 repeating, all right, which is the value of 5/6. All right. So nice little problem to begin with, alternating geometric series, our ratio, the sum formula. That's largely what we did yesterday. All right. And then the last one with this, general term here would just be considered a 1, and then all we have is that alternating sign. So if we look at this, if we think through what this is going to produce, if n is a 1, my first term is a 1. If n is a 2, I'm going to get a negative 1, positive 1, and it's just going to bounce back and forth between these. If I revisit real quick, up here, where I have the absolute value of our ratio better be less than a 1. I just want to give one more when it actually equals a 1. So this negative 1 is our ratio. Equaling that means we diverge. All right. So this was a 1. This one, then we say diverges. If it's less than 1, we converge. If it's greater than or equal to 1, you're going to diverge. Yeah, Lily, question? Okay. How do you feel about that? Not too bad. Easy stuff. All right, so that's our first way to determine if an infinite series is going to converge. If we go to the next page, this is the second way we can do this. Not every series you're going to deal with is a geometric series. So if we look at that very first problem that I have on the next page, this is not a geometric series. So we're not going to be able to rely on a geometric series test idea to work for every problem that we have done. All right. Oh, hold on. My bad. Go back to this one because I want you to justify this. So we're going to say diverges. This is the most important thing as we add all these tests. So you would say diverges, geometric series. Not an English guy. And then we would say with a ratio whose absolute value is 1, and that would just be it. Right, that's why we know it diverges. So that's our geometric series idea. That's how we can determine if a geometric series is going to converge or not. Our second test to determine if the series is going to converge or not. The wording here is important. We have something called the nth term test. The nth term test, notice how it says for divergence. The nth term test can only tell us if a series would diverge. It doesn't guarantee that it would converge. So we can use it to show that it diverges. It then says an obvious requirement for convergence is the last term, so our nth term, must be approaching 0. So what that references is this idea up here. This was a negative 0.2. Oh God, this is what, 0.04. I don't know what this is as a decimal, but aren't these each getting smaller and smaller and smaller? So the further on down the line, aren't those approaching a 0? That's the only way a sum could ever converge, is if slowly but surely all those are getting so infinitesimally small that they're basically having very little impact on our overall sum. So that's what the nth term test, or at least that first sentence, is telling us. So an obvious requirement for convergence is that the last term, or the nth term, must be approaching 0. If it does not approach 0, the sum would always be getting larger and larger and larger. So what this is saying is, if this is my infinite sum, it is going to diverge. We can conclude that it diverges if the limit as n goes to infinity of our general term fails to exist, so we get a D and E, or if it fails to be 0. I actually want to start with number 2 first, having done this for a little bit now. I think it's the easiest way to make sure we can differentiate what we did a couple of days ago when we did sequences versus now an infinite sum. So what I'm asking you to do says, why do the following series diverge according to the nth term test? So here's what you need to be careful of. The biggest thing to keep straight, you're going to use the nth term test for the next week and a half. Let's pretend this wasn't here. So a couple of days ago when we did sequences, we didn't have the sigma in front of us. And I would have asked you, all right, what is the limit of this as n goes to infinity? All right, what is that limit? 1. So don't write this down. But we would have said, when it's a sequence of numbers, which it is, if I get rid of the sigma sign, you would have said that this converges to 1. That's what we would have said if it was a sequence. I'll agree with that. Now it's not a sequence, though. Now it is a sum. So think about big picture-wise, some number sense here. Think about what that then means. Each successive term, as we start adding, isn't each successive term basically becoming a 1 if we say that the general term approaches a 1? Well, if I'm going to be adding all those up, wouldn't that make our sum just be getting larger and larger and larger and larger and larger? So that's what this is saying. If our series, or this is telling us, our series will diverge if the limit is infinity fails to equal 0. It has to equal 0. All right. So for this problem here, so now let's actually write this down. So you can write this down now. We would say that this series diverges. This is not a geometric series, so we can't write that. So what we would put is the reason we know that fails is the nth term test. And the reason that failed the nth term test is the limit as n goes to infinity for our general term. What did we say that this does converge to? The terms converge to what? 1, right? So the limit of the general term converges to 1 and not the 0 that it is required to do. This is how you need to write that. All right. All right, we good at home with that? All right. So now go to number 1. Same thought process. What the nth term test is really asking us to do is ignore the sum momentarily and identify what does our nth term approach as n goes to infinity? And it has to go to 0. That's the only option. So if I look at this one here and I have an n squared over a 1, will this go to 0? No. What is the limit of our general term here? Infinity, right? It gets bigger and bigger and bigger. So we're going to say that this diverges via the nth term test. And then we say what the problem with it was. And that was limit as n goes to infinity for that general term was infinity. You don't necessarily have to put not equal to 0. That's sort of implied. But we want to say that we knew it was supposed to be a 0. All right. So this one went to infinity. That was our issue. This one actually converges to a set number, but the fact that we're adding them is a problem. And then the third thing that could happen is number 3. So this one we know diverges. I'm telling you that it diverges. All of these are going to diverge. And they all diverge by the nth term test. And in this case, the limit as n goes to infinity for all those general terms. So if we started listing these out, we've already done this, right? On the previous page, the last problem on the previous page. What do we think the limit of that, we would say, is? Lily? And it? I was going to say the limit doesn't exist. Perfect. That limit doesn't exist. So let's go to those numbers that we had listed, right? I think I still have them up here. Didn't we get 1, -1, 1, -1? So our sum would be 1 initially. Our second sum would give us 0 if we add the first two up. The third sum is this. But each one of these is bouncing back and forth, back and forth, back and forth. So that limit does not exist. When you say it doesn't exist, you don't have to put the not equal to 0. Okay? So those are really the three things that could happen. However, and this is where things start getting a little bit loopy. Or, because you're going to have some options to choose from in the near future, and now this is our second option, couldn't we also say, like we did on the previous page, so if you ever see this problem, you really could use either one of these now. Couldn't we also say, and we have already said it today, wasn't this a geometric series with a ratio whose absolute value is a 1? So eventually, here's your series. Tell me whether this converges or diverges. And as we learn more and more tests here over the next week or so, you have to determine convergence, divergence, and which test proves that. Okay? All right, 4. Do 4 real quick, seriously. This one should be really, really easy, right? Because isn't number 4 written a little differently, but isn't it pretty much the same exact thing as number 3? They're both just going to bounce back and forth. -1, 1, -1, 1, -1, 1. So I'll be lazy. Either one of these explanations would work for this one as well. It's an nth term test because our limit doesn't exist and it has to equal 0. Or it's a geometric series and our ratio has to be less than 1, and this ratio's absolute value is a +1. So these end up being the exact same thing. So this is an alternating idea, and then it's recognized this as an alternating idea. All right, 5. Write down what you think number 5 here. A lot of things in play here. First of all, don't be fooled to think you're going to write this converges, right? Just by the directions I am telling you. Why do the following series diverge? So all of these diverge. Other thing we want to recognize is n plus 2 over n. Isn't that, if we split that into two fractions, n over n is a 1, and then 2 over n would be 2 over n to the n. So this is going to diverge by the nth term test. This is not geometric, so we don't have to worry about that. So this is the nth term test. And then we state what problem the nth term test had with this, and that was limit as n goes to infinity for our general terms. This was a sequence of numbers. What does that, so the sequence is going to converge, right? So again, this is another one you want to be careful of. This is the biggest thing to keep straight right now. If this wasn't here, so if I had given you this problem, I think I actually did give you this problem. If I had given you this problem without the sigma in front of it, as a sequence, you would say this converges, right? What does this converge to as a sequence of numbers? Remember this? Dara? You're really, 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 really warm. See this little guy, Daria? There you go. So this would converge to 2 overall, right? This is our natural log, the exponential function, that kind of counterintuitive function that you want to just get memorized. So this gets closer and closer to e squared for those at home that didn't hear Daria. And then we ultimately want to be taking the natural log of e squared. So overall, this is going to converge to 2. But now that we're doing this as a sum, that's a big problem. Because if each term becomes a 2, I'm really just doing plus 2, plus 2, plus 2 forever and ever and ever. That's why as a sum, it just gets bigger and bigger, you're going to diverge. So that's what we then say with our nth term test. Our nth terms had a limit of 2, which is not the 0 that it is supposed to be. Okay. All right, number 6. Go ahead and do that. There are 2 ways you could justify this. Do both of them. See if we understand how we can now justify these problems. This diverges. Write down both ways that we could determine that this diverges. In the future, you only need to do one. This time, I just want to see the 2 things that this unit covers. Do we know these 2 tests at this point? All right. Can anyone share one of them with me? Be confident in one justification. Brian, what do you got?
Diverges to the geometric series with the ratio 1.5 greater than 1.
Good. So he went with the geometric series idea. This is a geometric series with a common ratio whose absolute value he says is 1.5 or 3/2. All right, and that is greater than 1. So this is a geometric series. We're multiplying by 1.5 over and over and over and over again. That's greater than a 1. So if we go with the geometric series idea, this is really, really good wording of this. All right. The other way, we would say it diverges The only other way we know is the nth term test. So those are our two tests that this section opens up to us. And what do we say for that one? Now what's our problem? Now I'm curious if we know what this one is. Let me rewrite this a little bit, right? If I have 2/3 squared, don't I just square both of those and get a 4/9? So if I have 3/2 to the nth power, can't I really do 3 to the n over a 2 to the n? And then this brings back a couple of days worth of notes when we started doing this. So now as n goes to infinity, we want to talk about nth term wise, what limit does this have? So nth term test, limit as n goes to infinity. What did we say it was? Alex? Not quite one, because where's our faster growing function at? Top or bottom? The top, right? 3 to the n is going to grow faster than 2 to the n. So if the faster growing function is on top, Aaron, I think you said it, what is it going to be? Yeah, so that's going to give us an infinity. So the limit of this is infinity and not the 0 that it has to be. All right. So then that one kind of puts together pretty much everything we've done so far in this section with the rates that functions grow, your limits, nth term test, geometric series, all that good stuff. All right. All right. Here's what I am going to do. Since the person who hasn't taken it yet is not here.